Zurich Airport project, which is a large-scale complex timber structure. And I felt that this is a really relevant project for this overall discussion here because it's kind of a showcase. So I will talk about a little bit about the project, like what are the elements, what is the program, and what is the idea behind the design. And then, of course, I will talk about the computational design process within the project, how we are defining the geometry, but also the overall workflow with different parties and how we are envisioning it at the moment. And then, of course, a little bit of a excursus on the digitalization of timber construction industry and how it impacts us and how it impacts our workflow and the way we work on this project. So first, a little bit about the project. So I'm sure many of you must have seen this image. So the Zurich airport was inaugurated in the 1950s, and it is the largest airport in the country of Switzerland and one of the most important aviation hubs in Europe. And in the last couple of years, it has lost its competitiveness. So in order to be competitive on an overall global level and also to keep up with the growing passenger numbers, it needs to be reorganized, but it also needs to have allow for this increased capacity. So that was the overall idea behind the design competition, why it was started in the first place. And so the overall design approach is to have the dock, which is, of course, where the airplanes are attaching to the building, but also to have the root, which is the triangular structure, which is attaching the existing to the new. And it's a very restrictive framework to start with, to develop a new design, but it's also the complex framework is also really responsible for the design articulation of the project. So this is the dock, and as you see here, the structure is exposed and it's also defining the space. In order to develop this structure and the architecture, there is a very close collaboration between the architect and the engineer. Some of them are even here, not in the audience, but at the hackathon, who we are working with very closely. And the new dock, as you see it on the picture, has a very simple building form, and it has been derived from functional and operational requirements. So if you look at the cross-section of the building, you will see that the context and the constraints of the building are actually defining the overall form and the structural system itself, because so we don't have many columns going down to the ground plane, because it's actually used for operational reasons of the aircraft and of the handling. So that was a key driver for developing the structural system. And so, as I said, the constraint was to have a column-free traffic route on the ground floor, and that is also why this specific structural system has been proposed, because it's minimizing the columns. And of course, there's also a certain height limitation and distances, which are also driving the design expression in itself. Geometrically, it's very much characterized by these V columns you see on this image. And these V columns, they change in geometry and in angle along the building, which is also very, very spectacular if you look along the dock. So it's not just one straight line, but it's actually inclining. And it's also described by this linear skylight, which is also changing in size, and it's changing. It's like a free-form roof. I will show you in another image, which is quite characteristic for this dock. So the roof pitch is also lowering towards the west side of the building, and it's starting on a high pitch. Then, as I mentioned before, there is the root and the skylight, and the root is connecting the existing buildings with the new dock. It's a triangular node, and it has its very strong characteristic with the exposed timber. And the timber is an important topic for this project, like literally, because it's not only exposed as a surface, as a design element, but it's actually the load-bearing structure. And it's a unique project because this is probably the first time that a timber structure has been used in such an extensive scale for an infrastructure project and with such strong restrictions and constraints. And also it's, of course, contextual for Switzerland because this entire, these resources have been sourced locally and they're renewable. They are kind of important as a benchmark for Swiss architecture. And also they will have its own life cycle in the end of the building. So it's kind of also an ecological thought behind this project and a contextual local thought. So coming to the interesting bit, which is the computational design process. So the first question one would ask, why does this project need, or how can this project benefit from a computational design process, and why could you only design this precisely with a computational design process? So as you see on this image, there is around 1,700 unique elements. So how would you model this manually? It's quite complex. There's no repetition, hardly any repetition. And it's also important to say that the dock roof, for example, which you see with the pink outline, is a free form. So that is also driven by a script, and it's not easy or not impossible to manually model this to make it a data form or a geometry data, which can then be given to other participants in the project. So everything is very precisely defined in terms of the setting out, how this curve of the roof is developing. And also we have some local conditions, such as a sloping ground, which also makes the geometry a bit more complex, which means that together with the sloping ground and together with the freeform roof, each section of that dock is actually unique, and each element becomes unique. So it's changing from the east to the west, which is the difficult bit if one would think to manually model this. And then, of course, we have the skylight, which is a double curved skylight surface, which is also has unique bits which would be completely impossible to manually model this. So that's kind of the key reason why we have been implementing a computational design workflow, but also it gives us some added on benefits and some added on design implications. So as I mentioned, we have chosen or we have been implementing computational design workflows right from the start. So it started from developing the mass, evaluating the total area. And then from developing the mass, we developed the timber structure, which is all interconnected. And then, of course, all the elements which then come in the coming phases, such as developing the setting out of the timber structure and the structural simulations and the dimensioning, it's all connected to this one starting computational design workflow. And since we have been implementing these workflows, we have been identifying other other areas where we can also implement workflows for like layer analysis or glazing size optimization. So it's not just limited to our timber structure, but it has actually created like a different dynamic within the team, that many things are evaluated whether they can be solved by implementing computational design workflows. And this, I envision, will go up to the end, like even for the coordination and for the detailing, that it's kind of set up as a parametric computational workflow. So as I mentioned, it's all kind of a holistically viewed in our project. So this geometric interdependency is also visible in other parts of the project, such as starting from the massing, the volume. We also have not just parametrically developed the timber structure and the skylight, but things which are attached to it, so such as the envelope, or such as the fit out, such as the slab outlines and the ceilings. Everything is connected to that one workflow. So if something changes, if an inclination changes, it impacts the slab outline, it impacts the ceilings, it impacts the envelope. So everything is kind of interconnected geometrically, and nothing is done like by manually adjusting, but they are all attached to that one script which defines the geometry and the volume. Which also makes it, of course, important within the team to have this expertise, but also to communicate if something changes in one aspect, that it also is transferred to the other parts, such as envelope and slab and so on, that it's all interrelated geometrically. So looking at a brief sketch of the workflow. So of course we have a lot of input data, which is not just data, like written data or numbers, but it's also geometry. So for example, we have numeric data with levels and set-out points and dimensions of the structural sections, but we also have geometric data such as the grids, or we have volumes interconnecting or interfering with our building, which we need to consider. We have planes which we have added, such as the trimming planes for certain areas. So since this isn't on somewhere on a remote area with no context, it actually becomes a lot more complex to have this script working and to have this workflow working, because we have a lot of existing buildings which are connecting. We have a lot of specific situations within the building which need to be fed in as an input, such as volumes which need to be considered, or cores, or so on. And then, of course, one thing we've been discussing in our challenge group is the nomenclature. That's also something we input into the script, because at the end we will get a certain set of geometry data and element access, including the unique element nomenclature, which is written onto each element which is output from the script. So looking at the center, that's where the geometry is defined. But as the output, we get unique building elements, we get the axis, and we get insertion values, we get insertion planes and points, setting out points, and these are the data which we then share with our engineers, or which we will also envision to share in further, like in the next stages with other parties, hopefully to develop this project further. These are the steps of the workflow. So we start, just as a brief overview. So we start with grids and levels. Then we generate the intersection points between the grid lines. Then we have a 3D projection of these intersections to work points. We draw our vectors, or the element axis. We create planes which are based on the endpoints of these vectors, but also take the vector as a z vector. Then we draw the element sections at these planes. We project these element sections to the end plane. We loft and extrude. Then we do the inclusion test, or we consider interfacing buildings and slabs to get like an inclusion test. Then we do the trimming operation at defined locations. And then as an output, we get the final geometry after all these operations are done, with a unique naming, which includes the grid line, the level, and the element name. So we can identify this object within our model, we can locate it, and we can also use it for exchange with our engineer to have, so that they can map their structural data based on the naming which we agreed on. At a larger scale, this workflow, if you think about it, we develop the geometry, we give instance values to our structural engineer. They use it for cost calculation. They use it for creating their own model. And then we also feed in this data to the BIM model to create like an IFC coordination model. And then this, of course, generates a feedback from parties which are involved in this process, or even from colleagues which are planning the interior. And then this feedback is then fed back into the original geometry, but we are also envisioning more and more to get feedback back from fabrication and assembly companies. And there's still no clear idea how this feedback will be then put back into our model, but I think that's also a challenge we will be looking into in the coming time. But in an ideal scenario, there's like a interconnected feedback loop between us developing the geometry and defining the intent, then the BIM coordination process and the fabrication, that all these parties and all these involved people contribute to the feedback workflow, and that it also becomes like a closed loop in an ideal scenario. So this slide just shows all the uniqueness of the building elements and how they are generated in order to construct the entire structure. So you can already see the number and the uniqueness of each element. And then a little bit of a discourse why this development in the timber construction industry is important for us and how we work on this project. So as you know, I might not need to explain it, that there's a big historic development from manually cutting and assembling to a machinic assembly, which is also has had a big important history, and it's also impacting the way we work. So it also allows us now to model complex geometry, but also because there is a development in how fabrication is developing, it also allows us to construct this complex geometry. So there's kind of an interconnection, and in this way, this is an example from design to production. You could have curved beams defining a double curved surface, or you could have simple beams with complex nodes describing the same surface, depending on what your design intent is. And that's all just possible because of the development in modeling techniques, but also in fabrication techniques. And this actually is important for us because now we are able to model complex geometry, but we can also envision its construction, its fabrication, and that workflow again shows how we envision the coordination feedback, not just from the engineers and the different parties involved in the design and technical coordination process, but also from the outside, which is the fabrication and the assembly sector. So as a thought how this could look and how this could then be fed back into our initial geometry development process. So understanding this complexity and understanding the development, it clearly becomes a challenge working on this project, but it's also a very interesting opportunity for us to develop these workflows and also how we work together, how we communicate together, and maybe it's also benchmarking some sort of workflow which we can only envision at the moment, and it will materialize in the near future. Of course, lots of challenges. We already see it in one of our hackathon challenges that it's not clear how this workflow could look like, but I think that's a big opportunity to have a project like this where you can also test and try and develop standards maybe for the future. Thank you.